Hello everybody, we're going to go ahead and go through section 3.2 here, looking at logarithmic functions. Essentially, logarithmic functions are the inverse functions of exponential functions. So this is the inverse to the exponential function. Okay? Now, as I go through this lesson here, I'm probably going to go through it pretty quickly. I'm not stopping for questions or anything like that. So if you have any questions, write them down. We'll get to them next time in class. Also, feel free to pause it, think about it, rewind it, listen to each part again, and go back through it as many times as you need to make sure you understand it. Let's look here at the very first thing. It says the number 2 to what power gives 8? That's essentially what's being asked here with this 2 to the x equals 8. And the answer is x equals 3. So 2 to the 3 equals 8. So that one's not too difficult of one to solve, but some of these can actually be quite a bit more difficult to solve. And so we need to come up with a way to do that and enter the logarithm, which is going to be the inverse of that exponential that we just tried to solve there. So what we can say is that if y equals log base a of x, then this also means that x equals a to the y. All right, and essentially, if we have something like one or the other, we can swap back and forth between them by just kind of following that recipe that's right there. The first equation there is called a logarithmic equation. And the second is the exponential equation. Okay? You don't have to actually know how a log works. You just have to know that it does at this point. Okay? You don't have to know how it actually goes through and does what it does, just that it does it. And then notice something very important here is that with what's going on here, you notice the base of the exponential from the last section right there is a. That's actually called the base of the logarithm too, that those two numbers are going to match up. And then, of course, this number is going to match with that one and this one with that one. Okay, so location of base in each form. That's what I was just kind of doing there, but might as well just do it again here real quick, where x is x, a, and y. Okay? All right, so it's almost like you can just kind of do a switcheroo with those things and swap them around to get from one form to the other. I don't necessarily love doing it that way, but it does work pretty well if you just kind of memorize, oh, this one goes here and that one goes there, and it's kind of like a little switcheroo, like, oh, I just put a down here at the base and I move y out in front, and then x, I kind of made this difficult for myself, but x goes over there, kind of a thing, and that'll work for you. So let's take a look here, converting from exponential to logarithmic forms. So here we have 4 to the third equals 64. So 4 is our base, and we can do then the log base 4 of 64 is going to equal 3. So we just move that there, move that over there, move that down there to the base, and we've got it. Okay? If we look at the next one, b, it has a base of 1/2. That means we'd have a log with a base of 1/2 of 1/16 equals 4. All right, so just a simple conversions there. I'll leave letter C for you to try. Example 2 here, write each logarithmic equation in exponential form. So we're going to go the other way. So here we see that we've got a base there of 3. So 3 is our base. It's going to be 2 to the 5th power equals 243. So it's just a matter of moving that there and moving the base there. Okay, so it's just rearranging them in reverse order. So for this one, for example, we have a base of 2. It's going to be 2 to the x power equals 5. So that went there and that went there. All right, and I'll leave that last one again for you to try. Okay, here we're going to look at using the definition of a logarithm to solve and actually figure out what our unknown variable is. So if we look here, we have the log base 5 of x equals -3. We can't really solve that like that, but what we can do is rewrite this as an exponential and get 5 to the -3 equals x. Okay, so now we have something equals x. We got x outside of that operator and we can solve it. So this is x equals 1 over 5 to the third. And so that's x equals 1 over 5 times 5 is 25, times another 5 is 125. Okay, let's take a look at this next one. Here we have our logarithm with a base of x. So the base is our unknown variable. So if we look at this, what we can do is we can write this as x to the 3 equals 1,000. And now what we need to do is solve for that. And we can do that by taking the cube root of both sides. Wasn't a very good 3. Cube root of both sides, and that'll give us x equals 10. All right. This next one is a little bit more complicated, so I'm going to go ahead and do this one out for you instead of leaving it for you. But essentially, what we want to do is figure out is to figure out what there is going to be 0. So if we think about this, what we're saying is 2 to the 1. All right, what is that going to equal? That's going to equal 2, right? Which has to equal x squared minus 6x plus 10, which means we can solve for that. So we're trying to solve this. So x squared minus 6x plus 10, or actually, let's go ahead and subtract 2 from both sides, plus 8 equals 0. And now that's something we can factor. So x minus 2 times x minus 4 works there because -2 times -4 is 8, and -2 plus -4 is that -6, which means we get x minus 2 equals 0, which gives us x equals 2, and x minus 4 equals 0 gives us x equals 4. So at that point, it looks like those two things would work for us. They'd make that inside 0. But what we want to do here is we could just do a quick little check and kind of show you. So for the first one, if we do x equals 2, we get the log base 2 of, we end up plugging in that 2. 2 squared is 4, minus 2 times 6 is 12, plus 10. And does that equal 1? That's our question there. And so we check this out. This is log base 2 of 4 minus 12 plus 10. That's 2. And so it's the log base 2 of 2. And yes, that works. And so then let's check x equals 4. So this will be log base 2 of, we plug 4 in there, we get 16 minus 24 plus 10. And does that equal 1? And here we've got 16 minus 24 plus 10. That is also 2. So this is log base 2 of 2 equals 1, and that works. All right, so that was successful for us. All right, moving on. We can look at some basic properties of logarithms. I'm not going to go into proving these for you or deriving them out or anything like that right now, but they may seem a little weird when we do these, but it's because they are dealing with exponentials where, like, you multiply two exponentials together and you add their exponents, kind of a thing. So those rules kind of end up carrying over into this and look a little strange at times, but Log base a of a equals 1. This is essentially telling us a to the 1 equals a. So if the base matches what you're taking the log of, it's going to be 1. Log base a of 1 is essentially telling us a to the 0 equals 1, is where that's coming from. And then log base a of a to the x equals x. And this is essentially saying a to the x equals a to the x. Okay, so if it has the same base essentially, so note from at least from 1 and 3, okay, 1 and 3, same base. If it's the logarithm is the same base as what you're taking the log of, same base means they cancel. Okay, they undo each other, and that's how they are kind of opposites of each other there. Okay, if we look here at this next one, we have a to the log of base a equals x for any x. And again, this is just like the other one where same base means cancel. We can do that one right there. So they basically just undo each other. The log base a of a to the something, the log cancels with the exponential, and a to the log of base a, the a and the log are going to just cancel out and leave you with that x. So this is how they're inverse functions of each other. That's how they undo each other. So find the value of each of the following logarithms. So we have log base 7 of 7. Well, that, if we look at rule number 1 up there, is just going to be 1. Okay, if we look at B, log base 6 of 1, we're basically asking ourselves 6 to the what power equals 1, and that's going to have to be 0. This is essentially rule 2. So this is rule 1, this is rule 2. If we look at 3 over here, we can rewrite this as log base 5 of 5 squared, because 5 squared is 25, and this is rule 3, which is just going to then be equals 2. So that's rule 3. All right, if we go down here to D, log base 2 of 16, here we can rewrite this as log base 2 of 2 to the 4th. Again, this is rule 3, and it's just going to equal 4. So that was rule 3 again. Log base 1/3 equals 9, and we're asking ourselves essentially 1/3, right? So this equals something. 1/3 to the what power equals 9. And for this one, we can kind of just do a little bit of checking. Well, we know if we do 3 squared, it's going to be 9. But we also need this to not, we also need to flip this over. So looking and thinking of it that way, if we just do squared, it equals 1/9. But if we do 1/3 squared and put a negative on it, then that has the effect of not only squaring it, but taking the reciprocal, which makes it become 3 squared, which is 9 right there. Probably don't remember that. So this means that this does equal -2. Okay, so that one worked. Next, we have log base 4 of 1/2. Essentially, again, what does this equal here? Well, it's 4 to the what equals 1/2. And so how do we turn a 4 into a 2? Well, we can do that by taking a square root. So that's a 1/2 power. So 4 to the 1/2, that's a 2. That's a square root. But we also need to reciprocal it. So it's 4 to the -1/2 equals 2. And therefore, that's our answer. Just like that, okay? So some of these, it's a little bit of kind of guess and check, but it's guided or educated guessing and checking. So now let's take a look at the graph of the logarithmic function. So the graph of the logarithmic function is going to be, we can obtain it from the graph of the exponential function. So for example, if this is my exponential function coming up like this and asymptoting there, we can reflect that across the y equals x line, right? And reflect that over and get a graph that looks like this. And so this is the exponential graph, and this is the log graph, okay? And then, of course, that green line is the identity, which is y equals x. So what is the domain of our logarithmic graph? Well, you notice we're not getting over here into the negative side at all. So, and we're not even actually getting to 0, so we have to be non-inclusive of 0 all the way out to infinity, because this little arrow just keeps going on out to infinity. The range here, this is going all the way down to negative infinity, and this just keeps going up, and it's increasing slightly, but it is going up, and so it will go up and get every possible positive number. So this will be negative infinity to positive infinity. Notice the domain and range here are just flip-flopped for the exponentials. For the exponentials, the range was negative infinity to positive infinity, and the domain was 0. I'm sorry. For the exponentials, the domain was negative infinity to positive infinity, and the range was 0 to infinity. So they're just flip-flopped. We have one asymptote. We had a horizontal asymptote on the exponential function. Now it becomes a vertical asymptote. And it's at x equals 0. Some important points: 1 over a, negative 1. 1, 0 is an important point. And then, of course, a1 is an important point. So make sure that you know those points going there, where a, of course, is the base, right? Log base a, like that, where a is the base. So let's take a look here. Find the domain of f of x equals log base 3 of x minus 2. So if we look here, if we just look at the log of base 3, our domain is 0 to infinity. But we have this minus 2 that's inside the function. It's inside the logarithm. So that means that's a horizontal shift, and we do the opposite of what's there. So this will be right 2. So what that means is it's going to take our entire graph, and it's going to shift it over by 2, like that, which means that when I do that, it moves my vertical asymptote over, and so now my new domain is going to be from 2 on out to infinity, that way forever. So our new domain is going to be 2 to infinity, like that. Okay? And keep in mind, this is different than log base 3 of x minus 2. That would be a down 2 and then would not affect the domain, because that's only moving vertical, and the domain, of course, is the side-to-side x values. Okay, so let f of x equal log base 3 of x, and then we'll state the transformations that occur here. So here, this is log base x plus 2. When it's written this way, that x is the only thing that the log is being taken care of. If they wanted the 2 to be in there, it would be like that, kind of like this one right above where they put the parentheses around both, but they didn't, so that means it's just the log of base 3 of x, and then this right here is outside of the function and therefore is vertical, and we do exactly what's there, so it's up 2. For b, we have this negative out in front of it, so that means this is a vertical flip or a reflection over the x-axis. So all our old transformation rules still work here. And now this one, the negative is inside the function, and so that means it's a horizontal flip, which is a reflection over the y-axis. Okay? And you don't have to worry about the base 3s. That's not going to do anything for transformations. And so here you can see right there the transformations are occurring, showed in the pictures. All right, so next we're going to get into what is called the common logarithm. And this is the logarithm with a base 10. It's called the common logarithm. This is quite often what you see on a calculator. And essentially it's denoted by omitting the base. So in other words, log base 10 of x, we would just write as log of x. Okay, so that's what we're doing right there. We just omit that 10 there, and then it's assumed that we mean log base 10. This is very common because we have you have 10 fingers. Every time we count to 10, we start over, so we have a base 10 number system. And so it's very easy just to kind of omit that one. It shows up a lot. It saves you a little bit of writing. So if we look at the first one here, number 1 there, it says the log of 10. Well, don't forget, what that means is it's the log base 10 of 10. And so that's going to give us a 1. Here we have the log of 1, which means it's the log base 10 of 1. So that's 10 to the 0 equals 1, so 0. Here, x can be a real number, then log of 10 to the x, well, that's log base 10 of 10 to the x. So the base of 10 matches with the base of the exponent, so they just cancel out. And then here, where we have x greater than 0, then we have 10 to the log base 10 of x. Again, the exponential and the base of the log match, and so they'll just cancel out and leave us with the x. Okay? The next kind of very common type, well, that's the common one, but the next time that shows up a lot, that type of common, is something called the natural logarithm. And this actually turns out to be very useful in a lot of places, but it's the logarithm with the base e, where e is Euler's number. And so it's called the natural logarithm, and it's denoted by log base e of x is typically just, and I don't know why I do this, I think it's so that it really doesn't look like an in, but I always write that one in cursive, ln. Okay, now be careful with that when you're doing the homework and you type a capital I, it looks like a lowercase l. So just be very careful. This is ln. Okay, natural log. Okay, so L, that's an L, it's not a capital I. So I get that question on the homework quite often where they're like, I'm typing it in exactly right, and I have to reply and say, I think you must be typing in a capital I instead of a lowercase l. So it's a lowercase l and a lowercase n. It is not a capital I and then lowercase n. All right, and we read this as L n of x. Okay, another one which I can't say I ever really hear people say, but ln of x, some people will say, I guess. I really haven't met them, but I've mostly been told that other people say it. I've never really known anybody that actually does say it. So ln of x is usually what we say. We're just pronouncing the letters ln of, and then whatever you're taking it is. So let's take a look at this one. We have ln of e, so that's the natural log. So that's a log of base e of e, so they cancel out and just give us a 1. The natural log of 1 is asking us, again, that's a log base e of 1. That's going to be 0 because e to the 0 is 1. Here, we got another similar one, let x be a real number. Then the natural log of e to the x, again, the bases match because that's a log base e of e to the x. That's just going to be x. And then here, down here, again, the exponential base is e and the log base is e, so they match, so they cancel. We just get that. All right, so let's try these last few ones here. So evaluate each expression. We have e to the natural log of 4. Again, you have e, a base e for the exponential and a base e for the logarithm, so they cancel and just give us 4. Here we have natural log of e to the negative or e to the 2.5, which we can write as natural log of e to the negative 2.5 in order to get that reciprocal of it. And then at that point, it's just natural log of e. They cancel, and that's negative 2.5. Here, natural log of 3. This one you would have to type into your calculator, and I think you get about a 1.098. So that one, calculator. Okay. And then log base 10 of the natural log of e to the 1,000. Well, if we look at the inside part here, that natural log and that exponential of e, they're going to cancel. And so we end up with just the log of 1,000. And the log of 1,000 is log of 10 to the third. And this is a log base 10, right? That's a base 10 of 10 to the third, which is just 3. Okay? So that's pretty much it for this section. I hope this helps you out. And, if you have any questions on this, then be sure to ask me about it in the next class. Go back and rewatch any of this to kind of get a better feel for what I just talked about. And I will see you guys Friday. Thanks a lot.